Ladies and gentlemen, I'm excited to talk about our paper Prudent Evaluation Practices for Fuzzing today. I'm very happy that it has received a Distinguished Paper Award and would like to thank all my co-authors for putting in an impressive amount of work to make that happen. Now, we've heard multiple times the fuzzing hype train is over. There is no more chance for getting your fuzzing paper accepted, but if we take a look at how many abstracts on A-star venues feature fuzzing as a keyword, we can see there's no point in time at which there have been so many fuzzing papers as last year. So clearly, the hype of fuzzing is still ongoing. This has led to a huge body of research, many hundreds of fuzzing works, and such a large bubble of research has risks. In other fields, we have seen that this can lead to a replication crisis. So today we are looking into whether this is the case for the field of fuzzing. We are studying fuzzing evaluations. We see whether they are reproducible or whether there are other pitfalls that threaten their validity. Now, what we have done is we have looked for all the fuzzing papers on the 7 top tier venues in the security community. So ACM, CCS, IEEE, SMP, Usenix Security, and SoK NDSS. And the general software engineering community, so ASE, ICSE, and FSE. In the past 6 years, we've made sure to only include fuzzing papers that present a new technique and have a evaluation of the fuzzer. So not every paper that uses fuzzer is included, but only those that focus on improving fuzzing. This gave us a large amount of papers, around 300, and that's a little bit too much to study all of that. So what we did, we sampled 150 of these papers and conducted a thorough literature analysis. We've been reading these papers, we've been studying their evaluations, we've been noting down what's the setup, what experiments do they use, and whether there are any potential pitfalls. Now, for a number of papers, we noticed atypical stuff going on. So for some of them, more precisely 8 of them, we also tried to reproduce the results in practice. And with everything that we've learned from our literature analysis of the 150 papers and our 8 case studies, we've updated the recommendations. Now, when I'm saying update the recommendations, this must mean there are recommendations. And indeed, this is the case. There is a couple of papers that outlines how to evaluate fuzzing. But the most important one and the probably most known one is evaluating fuzz testing by Cleese et al., published at CCS 6 years ago. Now, for the sake of this talk, we stick to the recommendations of Cleese et al. And see how they worked out in practice. But before we do so, let me give you one huge disclaimer. We have absolutely no intention of blaming someone. We have absolutely no intention of pointing fingers. Our intention is to see how is the state in evaluating fuzzes, what are pitfalls, and pointing these pitfalls out so future work can avoid them. Our own works have also multiple faults, and we've definitely learned a lot throughout this project, and I'm pretty sure our future fuzzing evaluations will profit of this knowledge. Now, with that in mind, let's head to the recommendations of Cleese et al. First of all, we should document setup and parameters. This includes subtle stuff such as the versions of the targets or the fuzzers. This is rarely forgotten, but makes it difficult for others to reproduce your results. Then we need to sample relevant targets. And one aspect of this are benchmarks. Benchmarks are readily available and allow us to compare the fuzzers on a standardized set of targets. Now, there is different benchmarks, but some of them are considered to be outdated because they artificially inject bugs which do not represent actual bugs in the wild. As we can see, such outdated benchmarks are still in use, and the majority of papers does not use benchmarks at all. Now, this is not inherently bad, as many subfields of fuzzing, so to speak, have no benchmarks of their own. For example, firmware fuzzing cannot use fuzzbench because their type of targets is so different. Now, if you're doing a general purpose Linux user space fuzzer, you probably want to use fuzzbench though. The next recommendation is about the baseline to which we compare our fuzzer. And here, let's dive into one of our case studies. We had a new fuzzer that proposed two different things. First, they proposed to dynamically adapt the probabilities of choosing a particular mutation. For example, if bit flips would be excellent on the particular target, they proposed to change the probabilities so you can choose bit flips more often. And second, they proposed to use an evolutionary strategy to optimize these probabilities. Now, when we reproduce the results on fuzzbench, here for bloaty fuzz target, we saw the following results. The tool outperforms AFL by some margin. Now, one thing we noticed this paper was missing was an ablation study of their contributions. So what we did is we proposed an ablation where we would dynamically adapt the probabilities. However, instead of using the evolutionary strategy, we would randomly adapt the probabilities. When we include this ablation in the plots, we see the following picture. There's basically no difference. So let's zoom in. Here we do see a statistically insignificant difference, but on this target, the ablation performs better than the new fuzzer. Across the benchmark, this is not always the case, but the differences between the two are statistically insignificant. Meaning, while dynamically adapting probabilities may be a good idea, the evolutionary strategy did not work out as intended. Now the key lesson here is ablation studies are crucial to measure contributions in isolation. In particular, if we have multiple contributions, we cannot only measure the sum of them, but we need to look at the contribution of individual parts. Now, let's head to the evaluation metrics and let's speak about code coverage first, as code coverage is universally used. Here we have another case study which focused on improving input scheduling with the declared goal of covering more paths while using fewer inputs. When we look at the figure they had in their paper, they achieved their goal. Their fuzzer finds significantly more paths using fewer executions than its baseline AFL. However, when we try to reproduce this outcome using the standardized coverage over time metric, we see a different picture. Here, AFL finds more branches in the 24-hour period. Now, I'm not saying new metrics may be inherently bad, however, it is important to always include some known metrics so the reader is not misled by these new metrics. The second evaluation metric commonly used in fuzzing is bugs. Bugs are the gold standard. Our fuzzers are designed to find bugs, so it makes perfectly sense to use bugs for the evaluation. However, it turned out evaluating on bugs can be tedious, as we, for example, may not know the underlying bug distribution for real-world targets. So what people did, they use AFL's unique crashes as a proxy for that. And we had another case study where a fuzzer that proposed an additional feedback mechanism, namely memory usage, used AFL's unique crashes very prominently as a metric to prove they are superior than their baseline AFL. When reproducing the experiments for one popular fuzzing target, NM in this case, we found indeed their fuzzer finds 4 times the unique crashes than AFL. However, from this we have no idea about the true number of bugs found by both fuzzers. Fortunately for us, the developers had patched one of their bug reports. So we applied the patch and rerun all the crashing inputs, observing whether they would still crash. Any crash that would no longer crash was fixed by this patch, meaning it belonged to this one bug. Doing this, we find we are down from 1700 or 464 crashing inputs to 14 or 9 respectively. These unique crashes aren't so unique after all. Still, we are not 100% sure about the underlying bug count. We know there must be at least one, the one that has been patched, but what about the other unique crashes? So what we did was we manually deduplicated all remaining unique crashes, and we found in fact there's only 2 unique crashes for each fuzzer, meaning both found 2 bugs. And the thing here is this paints a significantly different picture. We are down from finding 4 times as much unique crashes to finding the same number of bugs as our baseline. The lesson here really is unique crashes definitely aren't as unique as we think, and they are definitely not actual bugs, and this already has been pointed out by Cleese et al. So we re-emphasize that there is a strong need to deduplicate crashing inputs, possibly involving manual work, to make sure they are actually unique, or even better, use bugs. Last but not least, we should statistically evaluate our results. Now, a necessary predecessor for running statistical tests is that we repeat our experiments, and we commonly do so, at least most of the fuzzing papers we have observed. However, many of the studied works would use less than 10 repetitions, which may not be enough to have a robust outcome for our statistical tests. Now, when looking at the number of papers that would run a statistical evaluation, we find most actually don't. And even if they do so, they usually just check for statistical significance of the results without measuring effect size. Now, this is definitely something where we can do better in future. So we should make sure to have at least 10 repetitions or trials, as they are called sometimes, and then use a test such as Man-Whitney-U or bootstrap-based test as we propose in our paper to measure significance, and the AHEAD-12 test by Varga and Delany to measure the effect size. But there's more than the evaluation itself. We've been talking always about the evaluation, but our work has also looked at other aspects, namely whether the fuzzer source code is available and what happens at new bugs we find during our evaluation. Let's start with the good news. Artifact availability, the fuzzer source code. Turned out, in surprisingly many cases, the fuzzer source code is available. Unfortunately, this does not yet translate to artifact evaluation participation, as many papers that had access to the artifact evaluation did not choose to participate. Now, if we already upload the source code to GitHub, it should be pretty easy to at least get the available batch, possibly even more batches such as the functional or results reproduced batch. In short, it's great to see so much code openly available, but I invite all of you to submit your work to artifact evaluation. I would like to point out though that artifact evaluation is a relatively new process which might explain this phenomenon. Now, let's talk a little bit about new bugs we find during our evaluation. What happens if we find new bugs? Well, we responsibly disclose them, right? So, to track this a little bit, we had a look at CVEs. CVEs are a unique identifier associated with a bug, making it pretty easy for us to see in the paper the CVE ID and then look up what happened. And that's exactly what we did. From the around 338 CVEs that have been assigned and been claimed by a fuzzing paper, only 133 of them have been fixed. A large chunk, 88, is in the so-called reserved state, where no public disclosure has taken place, so we have zero information on the underlying bug. More worryingly, 69 of these CVEs have been ignored. Some of them because the project where the bug was found is inactive, but many have been assigned to bugs in active projects, raising the question of why the project developers and maintainers have not reacted. And 36 of the CVEs have been considered invalid, either because they are a duplicate or because the maintainers considered the ported bug as not a bug or not a security bug, raising the question of why a CVE was assigned here. One explanation is the misaligned incentives. For a fuzzing paper, it is beneficial having CVEs. They are perceived in the community as a proxy for real-world impact. A fuzzer that finds CVEs, that finds bugs that are assigned CVEs, must have some real-world impact, right? Well, this is not necessarily the case. Not all CVEs are verified, so this opens a vector to game the system and receive CVEs of questionable quality. Now, if we think back about the recommendations by Cleese et al. And the aspects around it, there is a lot we can learn from this data. And from everything we've learned during our literature survey, during our case studies, we've updated the guidelines. More precisely, we have put a very exhaustive list of guidelines on GitHub. And my hope here is that you check it out and contribute to this list of guidelines so we find an exhaustive list that helps new authors properly evaluate their fuzzers and that helps reviewers check whether submitted works are reproducible. And with that, I would like to pass you the one key takeaway I've learned here, and that is fuzzing evaluations are simply damn hard to get right. It's pretty easy to screw up. So what I would like you to do to mitigate the situation is join artifact evaluation. Submit your paper, join as a reviewer, review other works, and help us with the guidelines. Check them out, see if you think something is wrong, correct us, send in a pull request. This will be very much appreciated. Thank you.